So maybe you have seen this paper, The Era of 1-Bit LLMs. Let's open the paper so you can confirm if you have already checked it out. This one, The Era of 1-Bit LLMs, all large language models are in 1.58 bits. And this paper basically shows that addition, that we can by using a 1-bit architecture for large language models, we, instead of having like a multiple bit architecture, so you have to encode each number of this large language model. So consider this matrix here. This would be like a large language model, right? A large language model is nothing but a matrix of numbers, and the numbers are usually floating point numbers. For each of those floating point numbers, like the top left one, 0.2961, this one would be encoded using multiple bits, maybe 8 bits, maybe even more bits, to encode this one number, right? And by replacing this architecture with where we have a matrix of floating point numbers with a matrix of integers with only 3 possible states, 0, 1, or -1, we can basically reduce the complexity of the whole thing by I would say almost an order of magnitude. We would see some evaluation results. And the question would be then, with this new computational architecture, I will do some explanation in a minute. The question would be, what does it mean for Nvidia? So let's dive right into the video.
Old gods crumbling in the dead of night. Want the riding high, redefining tech. Nvidia. Yo, the future's here, 1-bit chips revolution. Nvidia's shaking up tectonic confusion. Big gorilla in the room, 600 pounds of power. The 1-bit coming through, showering this gonna sour. Check it, 1-bit lean, Amina computing king. Nvidia's heavy, but we got that agile swing. Efficiency, precision, cutting edge like a blade. Big gorilla moves slow, innovation, my trade. Battling silicon, the tech titans clash. Old school heavyweight, new era crash. Nvidia, 1-bit, let the sparks fly. We the future, watch this giant comply. Bit is streamlined, every bit's like gold. Nvidia sweating that grip, and is bold. A new dawn in town, microchip supreme. Disruption in the air, the future's a dream. From the labs to the streets, tech wars ignite. Old gods crumbling in the dead of night. Want the riding high, redefining tech. Nvidia, just a relic broken in this trek. Battling silicon, the tech titans clash. Old school heavyweight, new era crash. Nvidia, 1-bit, let the sparks fly. We the future, watch this giant comply.
Okay, so I just needed to include this song. Sorry about that.
From the labs to the streets.
Good. Let's dive right into the paper. So the idea is the following: if you have this matrix here represents a large language model, as I said, right? A file of numbers, and these numbers are structured like in rows and columns. And if you do the training, you basically perform training and inference. You basically perform a series of matrix multiplications and additions. So it's like a heterogeneous mix of operations on the computing infrastructure, on the GPUs and CPUs. You perform this series of operations, like for instance here, we have this matrix and we have a row, which is the input, right? The matrix is W, the model, and you multiply it with the input. So you basically perform this computation 0.2961 times x0, as you know from school, minus 0.0495 times x1 minus 0.0924 times x2 minus 0.4765 times x3, right? So this would be the operation. So you see you have like 4 multiplication operations and 4 addition operations, right? Or subtraction, it's the same. So we need to do multiplication, right? But now the problem is first of all, multiplication is really complex. Yeah. So if you check out, integer multiplication always needs a carry propagate add step at the end. Consequently, addition is always faster because that's the final step of multiplication, right? Multiplication is much more expensive than addition, first of all. Second of all, you need a number of bits to encode each of those numbers, right? So you need, for this floating point number 0.2961, you need basically 8 bits at least, possibly more bits to encode this one number, right? Why is that? Because of the many digits, right? You need 2 to the power of 8 means you have, let me calculate, like 256 different states, right? So you can encode 256 different values. So even 8-bit would be, I'm not sure if this would be enough. Probably it would not be enough to encode this whole like 4-digit decimal numbers, but not sure about that. Okay, so anyway, the idea is to replace this giant matrix with a simplified matrix where each cell can only take one of 3 states, 0, 1, or -1. And obviously you save a lot of implicit state, a lot of memory, right? Why is that? You only need 1.58 bits. 1 bit would be enough to encode 2 different states. 2 bits would be enough to encode 4 different states, right? So 1 bit for 2 states, 2 bits for 4 states. But as we want to encode 3 states, the true number of bits that would be needed is 1.58 bit. Actually, I prepared a small slide. Why is it called 1.58 bits? It comes from entropy and information theory. In information theory, we calculate the number of bits we need to encode an operation, to encode like information. The number of bits we need is, if all the states we want to encode, so if we want to encode n different states, we need log of n, so logarithm of the base 2, so a natural logarithm of n, which in our case would be log of the base 2 of 3 is 1.58. So we need 1.58 bits. This is just, you can throw this in any calculator and this is the result. Why? And the reason for this is that we have an equal probability of each of those values, right? -1, 0, and 1. We cannot assume that one of those values has a higher probability. Actually, the calculation for entropy is a bit more complex, as you can see in this formula here above. You sum over all states that are possible values, x1 to xn. So you sum over all possible values, you multiply the probability of this value with the logarithm of the probability of this value. And you add everything and put this minus in front of it. So entropy, to adjust that the logarithm of a value smaller than 1 is negative. And so you get a positive value out of it, right? And only if the probabilities of each of those states are the same, you basically can collapse it down to the logarithm of n, right? Which is this formula here. This you can show mathematically that it kind of evens out, right? If you have the same probability, if it is homogeneous. Because now, first of all, you can like each of those have the same probability, and each of them has the same logarithm. So it's like it's an easy way. So for example, you can pull the probability out, and then you can pull it out from the logarithm, and you simply obtain. You can do the exercise. Just take a piece of paper and do it yourself if you don't believe it. Okay, so this is the reason why it's called 1.58. So we need 1.58 bits theoretically. In practice, this would not be possible, right? In practice, we don't have a ternary computing device, right? Or compute hardware. We only have binary hardware, so we would need at least 2 bits. But this is more like a theoretical result. And of course, even without specialized hardware, this has significant advantages in terms of memory overhead, because we could still use it, right? We could still use this kind of exactly same strategy. So here is the overall result of this paper. It shows that the performance stays the same, right? So the performance here is for BitNet B1.58, which is actually the paper using this 1-bit LLM scheme, is the same as having a 16-bit LLM. So you have significantly less overhead in terms of storing this model on your machine, and then also in terms of processing it, because in addition to the storage advantages and the advantage of not needing so much time for communication, i.e. loading the model from memory to your own computer, you also, in addition to that, you also don't need to do any multiplication operation, right? So you have like two big advantages in terms of memory and computation, which means the cost for this whole thing improves significantly. And sorry about that, I have now just get a call. Okay, so the advantage then, to sum up, is you need less memory to transfer the model parameters from DRAM to SRAM. DRAM is the slower memory, SRAM is the faster memory. And if you know computing, you know that the bottleneck in computation is often not computation, but communication. So you need to load the data from stable and slow to volatile and fast storage and back, right? And that's why you have CPU caching and all these different like GPU memory. And that's why Nvidia uses like this NVLink technology for fast communication and stuff. So it's often a communication issue, and the communication issue burden is also reduced if you have less memory overhead, because you need only 3 bits instead of 16 bits or so, right? Then also, in addition to that, we don't need to perform matrix multiplication, as I already said. So most time and effort in the traditional LLM training and inference is spent on matrix multiplication, interestingly, right? So matrix multiplication is the bottleneck, and we remove this bottleneck as well. Why do we remove the bottleneck again? Because here you see, if you have only ones, zeros, and minus ones, you basically simply need to add or subtract parts of this vector. If there is a 0 value, you can use a simple if then else statement, right? To differentiate between whether you want to add, subtract, or skip a certain cell of this input vector. The conditional statement is really fast in computing, and also the addition operation is really fast in computing, and there's no multiplication operation to be seen if we use this approach. Okay, so and in practice, you can see now the evaluation results. They are very promising. They show the latency on the y-axis and the memory on the y-axis improve by half an order of magnitude, right? For different model sizes, and the performance, there's no performance loss basically. So it has the same. The models have the same performance. How do they get from this matrix to this matrix? It's like this is a process called quantization. We don't need to look into it, but it's like a glorified rounding numbers up and down, I would say, right? I mean, of course, there's more to it, but it's just like for each of them, you see like this 0.29. In this case, we round up. Here we have a minus value, so we round down to minus. If it is like very close to 0, then probably we would. Yeah, it's in this case it's not even true, right? So that's why I said glorified, because there's a lot of science to it. But generally, there's some correlation, right, between simple rounding up or rounding down. You could just round up and round down and look at how the model was working. It wouldn't work as well. But quantization is just this approach of reducing the complexity of each value, reducing the information encoded in each value, and if you reduce it the right way, you don't lose a lot of performance. Okay, so the performance would be worse, but not so much worse, and it is actually not measurable in the paper. And then another huge advantage here is that we have significantly reduced energy overhead, right? Here, by a factor of 71. in this one example, right, which is a huge advantage, because energy is one of the most expensive cost drivers of any data center. So we have significantly less energy usage, memory overhead, and computation overhead. We have speed up gains. So the question would be, what does it mean for Nvidia shareholders who bet everything on this fact that Nvidia is able to sell GPUs that are currently used for training and that are optimized for these floating point matrix multiplication operations that run in parallel on a GPU. And even the paper mentioned that this research opens the door for designing specific hardware optimized for 1-bit LLMs. Right, hardware that, for instance, would then encode each of the states of this matrix, like with a ternary bit, right? Something like this. Yeah, ternary, like not a binary bit, but a ternary bit. This would be like the perfect hardware for this kind of approach. So there are many implications that are also mentioned in the paper. For instance, it could have implications for a mixture of experts models where you have many small expert models. Each of the small expert models is trained on a specific sub-area, sub-data, and each one running on a single chip. So you don't have any communication overhead as you run this whole model on a single chip, right? And so you can totally reduce inter-chip communication, which makes it really efficient. And then you combine their results together. So you have the different smaller experts, you combine their results in an intelligent way by averaging or whatever. Maybe weighted averaging approach, maybe something even more intelligent, a hierarchical mixture of experts model. So you combine the results to obtain the final result of your inference or training operation. And so this could be one implication. Another implication could be to have a 1.58-bit LLM for edge and mobile applications. And edge and mobile, edge computing means everything where the computation is actually performed close to the application itself. An example of edge computing would be a self-driving car, right? So the car itself is doing the computation. The car doesn't send the camera data into the cloud and performs the computation in the cloud, like the inference, for instance. It performs the inference like right there on the car. We humans are also like edge computers, right? We perform our inference in our brains. We don't like send all the informations we have to the President of the United States and let them do the computation for us and give us the correct output. We do it ourselves, right, in our brains. So we are also edge computers. And many argue that we will have orders of magnitude more inference computations than training computations themselves, right? So we have some amount of training, so we train our brains, and then we have some amount of inference. So we get we use our trained brains to get a specific action in a specific situation. So we ask it for the correct decision, and it gives us the correct decisions. And obviously there are like new companies now like Croc that focus on inference and that create new hardware chips, or sometimes called language processing units, that are optimized for large language models. And yeah, so where large language model inference is first class citizen. Okay, so like one question would be like Croc versus Nvidia. Croc focuses on inference, Nvidia focuses on training. It's a very like crude way of looking at it, and there's some argumentation, so I've read somewhere online, that Nvidia and AMD are not novices. Why don't they use SRAM for memory like Croc, like the fast RAM, which is the reason why Croc is superior for inference. The reason is that simply that they focus on inference, right? And for inference, you can afford to use less data, basically. Yeah, so you see today 80% of AI China's demand for computing card is focused on training, with inference demands being much smaller. Compared to inference, training requires more stringent computing card specifications, especially in terms of memory size. So for training, we need larger memory, which is the reason Croc basically doesn't work for training. It works only for inference. So Nvidia will still remain the 600-pound gorilla in training. Basically, this question is kind of independent, but of our question, how 1-bit LLMs impact Nvidia. And I think there will be an impact, definitely, right? But let's maybe still focus on this one quick discussion: Croc versus Nvidia. Here we can read Chia Changqing, former vice president of Alibaba, made a comparison. Under the same throughput conditions running inference for Llama 2 70B model, the hardware cost of using Croc's hardware is 40 times that of using Nvidia's H100. And the energy cost is 10 times higher. So Croc is actually not, the competitors are not so fancy as many people argue, right? The competitor, it's not like Nvidia doesn't see it, right? It is like I have highlighted here, Nvidia and AMD are not novices. So they know the game, they know the trade-offs, they know everything in this kind of space. They have done it for 20 years, Nvidia has done it for 20 years. So while there are potential like inefficiencies of using Nvidia GPUs for 1-bit LLMs, and maybe let's go into those inefficiencies first. While there are those inefficiencies, there are easy fixes, and I'm pretty confident that Nvidia will just adjust on the way. Okay, but let's look at the inefficiencies. The inefficiencies are that Nvidia GPUs are optimized for floating point operations. So we have 16-bit and 32-bit operations, and 1-bit operations like or 1.5-bit, 58-bit operations like the ternary values are less efficient on the specific hardware. We don't use the high bandwidth for floating point, right? Because we have significantly bandwidth to send these bit of data units, send it to other computational units, right? In the GPU, we actually send floating point numbers back and forth between computational units, which means we would have to have significant bandwidth that we won't use then. So we would over provision in terms of bandwidth, which would be expensive. And also we have software libraries like CUDA and cuDNN that are optimized for floating point and not for like sparse operations optimized for these 1-bit needs. So these are the inefficiencies. They are definitely there, but now you could ask, is it the death of GPUs? I would argue no, not at all. GPUs are like conceptually they are better for these highly parallel tasks. And even if you remove the matrix multiplication operation, the addition and subtraction operations are still highly parallelizable. So we still need to parallelize the computation. So it changes nothing from first principles. And I've even prepared this video here, which is really fun. So this one is a GPU gun, a CPU gun, right? So here you see the CPU actually here it shoots this different. Each shot is like a computation, right? It represents a computation, and now they uncover their GPU machine.
Into these tubes, in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space.
So each of those would be like one core, right? So the paintball is the paintball we have seen earlier.
80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
And 10,
9,
8, 7, 6, 5, 4, 3, 2, 1.
Okay, so you can see it is still this parallelizable GPUs are still valuable even for 1-bit LLMs from first principles. And of course we will see application-specific hardware as we see in any application, especially for applications like large language models. But Nvidia has already built AI-optimized training and inference hardware that is tightly integrated with CUDA, and they will just continue to do so. And basically their strength is to optimize the trade-offs. And they already have like inference hardware. They already work on inference hardware as well. And they will simply execute those steps. It's just a matter of them executing those steps to fix the specific inefficiencies we have seen previously. So they need to implement custom kernels and libraries, they need to design specialized hardware, and they need to integrate hybrid approaches. But with Nvidia, you basically bet on an innovation engine that has proven to adapt, innovate, and lead in new AI hardware for 2 decades. We already know that they need to innovate in terms of hardware, and this paper changes nothing in terms of this assumption, right? It just proves the point that Nvidia is an innovation engine. It is not their GPUs today that will be the GPUs of tomorrow, right? They will need to design new GPUs. We already knew this before the paper. So Nvidia is still the undisputed leader. They are tightly integrated into every cloud provider like AWS and Google Cloud infrastructure. Most AI training already runs on Nvidia. They have the biggest brand. All AI researchers know and love Nvidia. They have a killer mode, and I've done a video about Nvidia's mode, and they are still the industry leader in AI. Competitors can only dethrone them if they can actually provide something that's 10x better, and because of the network effects and the tight integration with the real world they already have, and they cannot be copied easily by Nvidia. And this second one is the problem, because Nvidia, if there would be a simple solution, they would just Nvidia would just basically copy it, and then the competitor would be dead, right? And now the second question is, will 1-bit LLMs lead to less hardware demand overall? No, not at all. We have the AI scaling laws. Even if you become more efficient, it is still true that using more compute, using larger data sets, using more parameters, yield better performance. And this is kind of we need to throw a lot more compute, a lot more data, a lot more parameters at the problems. Even if you get a 10x improvement, we will just use 10x more compute or 10x larger models, right? So this kind of will remain to be true in the future, so it won't change a thing. Good. If you like this video and you want to stay on the right side of change, then give me a like, subscribe to this channel. You can also check out our free newsletter. Just go to finxter.com, visit the newsletter. You can check out our AI engineering courses on academy.finxter.com. The main purpose is to show you how to use these AI tools to be on the right side of change, so you can create massive scalable value that you couldn't create otherwise. So check out academy.finxter.com, finxter.com, to subscribe to our courses. You can certify your skills, prove it to your employers or freelancing clients. And you can also become a channel member and access all Academy courses as well. Give me a like, subscribe to the channel, and see you in the next video. Bye.